in lab that we had a generator which approximates a DC source with a resistance, even though it's not really quite a direct current source, which is why you want to observe it. If you observe it with a fancy electronic meter, you want to observe it with a analog meter as opposed to a digital meter, because the actual voltage produced by these crank generators is not steady, so that a digital meter will give you readings all over the place. Anyhow, we have a meter and a source and a resistance. In this case, it's a generator, and there's an inductive reactance instead of resistance, and it's not constant. So that can present a problem, but for the purposes of what we're doing here, this generator works as a good DC source. If you crank it at a constant rate, then you get a constant, or a very nearly constant voltage. Your average voltage over any reasonable time interval, more than a few milliseconds, is going to always be the same. Okay, or relatively stable. We create an ammeter. Now, the first ammeter we created was a aluminum foil strip between two magnets. And another ammeter could be a compass over a wire, compass sitting on top of a wire in the electromagnetic, or the magnetic field of the Earth, and the result of a current through the wire if we have things aligned properly, or if we don't have them aligned improperly, is going to be a deflection of the magnet, or a fancy electronic meter that you don't know how it works, but it gives you much better readings. The better the meter, the better the readings. Okay, still, fancy electronic analog meter, better for this particular source than a fancy electronic digital meter, which is pretty useless in this case. Okay, well, we measure current just running through this. And then we do the same thing, but we put a resistance in here. Now, that resistance is a length of nichrome. So at nichrome wire, and we look at how different lengths of this wire affect the response of the ammeter. So that's one thing we observed. Now, a couple of definitions that we've already done in class, had already done prior to the lab. Actually, we hadn't done the amp. The amp is a fundamental unit. We can measure it more accurately than we can measure coulombs. But if you can measure amps, you get an indication of the coulombs. If you measure amps for a given time, you multiply the number of amps by the number of seconds, you get the number of coulombs that have passed a point in the circuit. Formerly, coulomb was regarded as a fundamental unit. We thought we could measure that more accurately than amps. It's no longer the case, so amps is now a fundamental unit. But an amp is just a coulomb per second. It's how much charge passes a point in this current, like passes this ammeter, in a second. A volt, as we've seen, is a joule per coulomb. And you want to understand these units and how they work together. Electric field, remember, is force over charge. That's in newtons per coulomb. Voltage is electric field times length, if you have a constant electric field, as you do in a wire if you put a voltage on it. So let's look at how that works. Okay, if we've got here's our length of nichrome, and we create a voltage across it by cranking this generator. Then, if this is a uniform wire, the electric field in the wire will be uniform. Now, it's hard to see, I think, but I've got little arrows in here indicating the electric field along this wire. It's uniform. It's the same at every point. If we multiply that uniform electric field by the length of the wire, we get the voltage. Now, this is very consistent with the way we've defined voltage as the work per unit charge. So voltage is defined to be work per unit charge. Electric field is force per unit charge. If we multiply work per unit charge by length, we get what? If we multiply force per unit charge by length, we get force times length, which is work per unit charge. Okay, so there's our relationship. So what we can observe, or what we can think of, if we think of this nichrome wire as something that spreads out the voltage, and the amount of spread of the voltage is the electric field. Now, if you're conducting charges, that means you're causing electrons to drift along this length. Now, we haven't gotten into the reason we talk about electron drift and so forth, but the electrons are bouncing around like particles in a gas, but much faster. They're free in here and they're bouncing around. So what happens if you have an electric field? It accelerates the electrons. Now, if the electric field's in this direction, the electrons are going to be experience a force in this direction, the opposite direction to the field. And between collisions, now the electrons are always colliding with each other and with molecules and so forth, or atoms, whichever it is. The collisions happen very frequently, so the electrons don't get to go very far before they get scattered. They get bounced in all possible directions. But the net effect of this is to make electrons drift. Now, the bigger the electric field, the faster the electrons are going to drift on the average, because the greater the change in velocity they get between collisions. So that's what a current is in a metal wire. Now, in other in other materials, it might be the holes that are moving, and the holes will move in this direction because the holes are positive. Or in a diffuse gas, we might have ion conduction, and ions could move in either direction. If they're positive ions, they'll move in this direction. If they're negative ions, they'll move in this direction. Either way, you get a current, and conventional current is in this direction. It's in the direction of the electric field. It's in the direction in which a positive charge would be accelerated here. Okay. So that's kind of a picture of the kind of things we talked about. And then we talked about the idea of resistance, resistance to the flow of current. So you'll have made some observations on what happens if you got a greater resistance to the flow of current when you have the nichrome wire in here, or less. Longer nichrome, shorter nichrome, greater effect on the current. And would you then say that the longer or the shorter nichrome has more effect in limiting the current, in other words, in resisting current as a result of the voltage you're producing here. We also looked at the resistance of the copper leads, and there were observations regarding the resistance of the copper leads. We looked at copper leads, chains of different numbers of copper leads. Did we see what sort of response did the ammeter reveal in relation to the length of the copper leads between here and here? Okay, and of course these solid wires here, solid conductors, represent the copper leads. Is there resistance in those copper leads? There's significant resistance, and if so, how do we deal with it?